Hey, I'm really enjoying the new digs, Jono. Great pool. How'd you pull it off?
Well, you know that TARDIS, Kev? In addition to getting my 99 HD, making sure that footy season's tracking okay, I went and pulled off another mission for the professor in that quantum mechanics course I was telling you about.
What, you mean the one with the craziest demo in the world thing?
Yeah, but this time we wanted to do the world's most expensive demo. See if we could take things to like a whole new level.
So, what was the demo, Jono?
Well, we wanted to use a real working quantum computer and program it live via the internet.
Wait, but can't you do that already anyway?
You can, Jono, you can, but only because we set it up that way. So let me tell you how it went. We had a few spare Dogecoin left over from the Alpha Centauri thing. They're only worth 30 cents right now, but Elon and Snoop Doge, they weren't kidding about it going to the moon. We went 100 years into the future in the TARDIS, and the Doge, it's worth about $100 million a coin in 2121. So we took our Doge and we bought a quantum computer, brought it back, stripped it down, worked out some of the key IP for quantum computing, and we accelerated the process a bit, if you know what I mean.
What, so you built the first quantum computer?
Not exactly. Who needs fame when you can have money, right? It takes a lot of resources to get something like this off the ground anyway, especially for a kid from the wrong side of the tracks like me. Nah, what we did was go back to 1990, buy a bunch of shares in certain companies on the cheap, jump forward to 2000, and, well, let's just say we started delivering bits of the IP in unmarked envelopes to them in the mail. Bish bash bosh, cruise on back to 2021, take a look at our share portfolio, and, well, everyone else's Dogecoins might be worth 30 cents, but with the rent on this palace, you can be pretty sure our Doge is worth a few orders of magnitude more than that, eh?
Stellar work, Jono. Well played.
Yeah, amen to that, Kev. And as a bonus, we're about to take home the record for the world's most expensive physics lecture demo, with some help from our friends at IBM. Not a bad outcome for a 6-unit accredit course, I must say. Who needs wham boosting when you can have this?
True, Jono, true.
Welcome to Lecture 13, which for this year of the course is an optional lecture on quantum computing for beginners. In past years of the course, when the term was longer, I had several additional lectures beyond the 12 that I've had in this year of the course. And one of them was, right at the end, it was this lecture on quantum computing for beginners, where we took a lot of the ideas that we did earlier in the course that go back quite a long way historically, and literally connected them to very modern day application of development of quantum computing technology. As the terms on my campus have shortened, I sort of ended up having to sacrifice a lot of these extra lectures, and this was one of them. And I've always felt really sort of sad about that, because it's nice to be able to take ideas that are very foundational and perhaps feel slightly old and connect them directly to things that are very relevant very now. And so what I've decided to do to resolve that is basically make an optional video lecture version of this, both for my own students and I guess for anyone who's generally interested in quantum computation, because a lot of undergraduate courses you'll see won't touch this subject, particularly in the introductory levels. And so I guess this lecture is probably a little bit of a community service as well, because it kind of gives a first insight to quantum computation. And we're going to do it in 2 parts. So I'll start by talking very briefly about qubits. If you've been following my course, they will more or less immediately make sense. We're just connecting an idea to them. We'll walk our way through a few simple quantum logic gates just to get a feeling for how you implement logic in a quantum perspective. Then you can just build up and build giant algorithms and circuits. And I'm not going to go into that because it would be an entire separate course. And in the second half, what I'm going to do is what I like to call the world's most expensive lecture demonstration. So what I'm going to do is use IBM's quantum computer, which is publicly available on the internet, and do something that's sort of the equivalent of a Hello World bit of coding just to demonstrate how to get in there, how to use it, how to see a result, and then people can sort of build on that themselves to go away and have a bit of a play with building their own quantum algorithms if they want, for a bit of fun. Okay, so with no further ado, let's get some slides up. Okay, so let's start with qubits. If you deal with classical logic, you've got the idea of a bit of information, which is a 1 or a 0, and you put it through a series of gates like AND or NOT or and so forth, and you build these up to do logic operations. If you do a quantum mechanics course, you realize that you've got a single quantum spin and it's got two possible states, up and down. And so an idea that might pop into your head is, hey, what if we connect the 1 and the 0 from classical logic to the up and down? Then we might have a way of doing quantum logic. And if we extend this idea, we might be able to come up with computational schemes that perhaps are more powerful than classical computation. So this is where this basic idea comes about. So let's start first by just defining this really well. The first thing you have to watch out for when you do this is how you connect the bit to the spin. And this can vary from place to place a little bit. And I'm going to choose the convention that follows both what's very common in the field and also my favorite textbook, which is the really thick Nielsen and Chuang, or sort of Bible of quantum computation. So what we're going to do is define our logical 0 as our spin up state and our logical 1 as our spin down state. And just a quick warning on this: if you're reading around and something starts to feel weird about this, it's probably a good idea to just pop back and check what they make the 0 and 1, because some places will decide arbitrarily to do that different because that's their preferred way of doing it. Okay, but the common convention is to do it this way. Now, one thing you have to be aware of is A, where the power of quantum computation comes from, and B, how to see through the hype. So where the power comes from is the idea that instead of just having a 0 and a 1, what you can have is a state of a system that is some superposition of 0 and 1. And if you have multiple bits, you can put them into entangled states so that they're correlated with each other. What you can then do is basically build links between all of your bits in the problem. And then in the end, after manipulating those spins, do a measurement and look at the outcome of the state of all of those bits, and use that with some clever ideas on logic to solve problems. Okay. Now, seeing through the hype, a lot of things that you'll see floating around the internet will be all, quantum computing is going to blow classical computing away, and we'll all have quantum computers and they'll be 1,000,000 times faster than every classical computer. The reality is that there are only certain subset of algorithms where you really do get useful speed increases out of a quantum computation approach. Okay, for a lot of things, a quantum computer is not much faster than a classical computer, and there's not much point in doing it that way. The reason why quantum computing has become such a big area of investment is that there are some very, very crucial algorithms that you can get a speed increase by using a quantum approach. Okay, probably the most famous one, and the one that's driven most of the investment, has been encryption. It's basically factorization of numbers. Encryption for everything in data security in the world is done by, essentially, you make very, very large numbers that are very hard to factorize, and you rely on the fact that it takes almost forever to factorize those numbers. You can get speed increases by using quantum algorithms to factorize numbers. And that puts, if you're interested in security, that puts you in a little bit of an arms race, because what you want to do is try and break encryption, and then on the other side, try and make it stronger. And then when it's stronger, you want to break it, and so forth, right? And so a lot of the investment in quantum computation in the early days came from sort of, military and intelligence organizations trying to make sure that they couldn't have their codes broken by the enemy. There's other places where you get speed increases. So for example, some search algorithms and so forth, you can get a speed increase out of a quantum approach to it. And sort of as the years have gone on, people have started to realize there's more and more little places where you can get speed increases via a quantum approach. And that's driven a lot of the interest and funding driving quantum computation as a technology. Okay. Once you're clear on that, you realize that actually quantum computation is not a catch-all for everything. It's a speed increase in a limited number of applications, but those applications are extremely useful, and that's what drives it, okay? And so it's all driven by this power of not just having 1 and 0, but having intermediate states as part of your computation. With qubits done, the next step is to take that up to logic. And one of the tricky things with logic is that it's part of a giant pile of pieces in computation that go from bit to logic to circuits to machine code to operating systems to applications and so forth. And in computation, often what you see is really only the highest level. So if I take my iPad, for example, I will see the applications and I might even see the operating system, but then underneath that is multiple layers that are kind of hidden from view that get all the way down to building sequences of logical operations on bits of information, okay? And so what we're going to do today is kind of unpack that. What we'll see in the second half is essentially what would be sort of the operating system level for quantum computers at the moment, which is like the Qiskit package for Python, that then would have a whole pile of code underneath that that would drive, you know, all the way down to circuits and read out on a real quantum computer. But ultimately, then at the very bottom level is taking bits and doing logic operations on them. So let's start with the simplest possible quantum logic gate we can have. You remember back to classical logic, you can have logical operations that act on a single bit, and there's only one of them in classical logic, which is a gate called NOT. All it does is take a 0 and turn it into a 1, or take a 1 and turn it into a 0. Essentially, it flips the state of that classical bit. And the reason why there's only one gate is because there's only 2 possible states for the system, and there's a very big limit on what you could have as logic gates. In our quantum system, as we saw 2 slides ago, we've got an up and you've got a down, but you've also got an infinite number of possible states that are superpositions of up and down. And that means that you can have a very large number of single qubit logic gates. And one of them happens to be the direct analog of the classical NOT gate, okay? There's that large number of single qubit operations is very powerful, and I'll talk about some examples of that later on without getting into too much detail, but I want to just drill into this one as the first example of a proper gate because it's very simple to deal with and you have a classical analog for it, okay? So the quantum version of classical NOT gates called quantum NOT, and it's often denoted by the letter X, and it's denoted by the letter X because every single gate or logical operation in quantum computation is connected to a mathematical operator. And in this particular case, the mathematical operator is identical to the operator we saw back in lectures 5 and 6, sigma X. And to keep the notation nice, basically, we don't care about the sigma, we just care about the X. So this thing has been called the X gate, okay? That's often why it's called that. What it does is if you have a qubit 0, it will flip that to qubit 1, and if you have a qubit 1, it will flip that to qubit 0, okay? So what it does is basically just swap from 0 to 1, just like in the classical case. If you have an arbitrary state, what happens is a little bit more complicated. You now have X acting on, for example, a superposition state, and when that acts on that superposition state, what it basically does is swap the prefactors. Let me just show you quickly how this happens. We'll need some writing paper up. We're going to have our state psi in here, and it's going to be alpha 0 plus beta 1. And of course, we know that there's a normalization to this. So alpha squared plus beta squared is equal to 1, okay? And all the way through this, we're going to have everything normalized so that everything behaves really well. If we take our operator X and apply it to psi, what we will get is 0, 1, 1, 0. Applied to our state just here, beta 1. And if we do this, this thing is really just 0, 1, 1, 0, alpha beta. And if we do this, the multiplication, it's going to be 0 times alpha plus 1 times beta will give us beta on the top. And 1 times alpha plus 0 times beta will give us alpha on the bottom, like so, okay? And so this thing is now written as beta 0 plus alpha 1, okay? So all it's really done is taken the prefactors and swapped them on the bits. Or the other way of seeing this, if you want, is to write this as alpha 1 plus beta 0. What it's really done is taken the 1 and the 0 and swap them around, okay? And so this is sometimes what we call a bit swap operation in quantum mechanics for a single bit, okay? All right, we can demonstrate that this works back on itself real quickly. So let's call this thing now a new state psi dash. If we operate x on psi dash, this thing will now be 0, 1, 1, 0, beta alpha is equal to, so now we go 0 times beta plus 1 times alpha is alpha on the top, and 1 times beta plus 0 times alpha will be beta on the bottom, like so. And we can see that that's now back to our original state, okay? So swap bits, do it twice, it will swap you back again to what you had in the beginning, all right? Now, same as you do with classical logic, what you have is you often have these built into circuits where your bits come in from the left-hand side, go through a gate, and then come out the other side, okay? And so for a NOT gate, you would have, bit comes in, triangle with a circle on the end of it, comes out the other side, and that thing represents the operation of that gate. Same thing happens in quantum computation. So we would have bits enter from the left, come through gates, which are just visually represented by symbols, and emerge as states on the right-hand side. Okay, so time flows from the left to the right. Every single gate has a particular little symbol to it that indicates what it does. And each of those logic gates then has some matrix operator that enacts mathematically what happens to that particular bit in that case. So that's our first simple, direct, classical analog single qubit gate. So now what we're going to do is jump to our first single qubit gate that doesn't have a classical analog. So it's actually our first gate with true quantum functionality. We're still dealing with a single qubit here, okay? What it does is convert a basis state into an equal weight superposition. And if you have the equal weight superposition, it converts it back into a basis state. Okay, so this is a very useful logic operation you can imagine already, because it enables you to make and break superpositions. Okay, this thing has an operator called H, which you've got to be a little bit careful to not call it the Hamiltonian. It's one of those things where you just have to rely on context to know what you're doing. And so if you apply this gate H to a spin 0, what it will give you is a superposition of 0 and 1. So 0 plus 1 over square root of 2, just to keep your normalization. And if you apply it to a 1, what it will give you is 0 minus 1 over root 2 to keep your normalization. Okay, and if you take some arbitrary state in here, what it will do is produce you some nice superposition in here. So let's just demonstrate that this gate also works as advertised. So what we do, let's do the case of just applying our Hadamard Gate to our 0 state. This thing has a form, and I won't go and calculate it directly, that looks a little bit like this. It's 1, 1, 1, minus 1, and the 1 over root 2 out the front is basically just to conserve normalization. So this thing would be 1 over root 2, 1, 1, 1, minus 1, 1, 0. If we do this, keep our 1 over root 2 out the front. 1 times 1 plus 1 times 0 is 1. So that's going to give us a 1 on the top. And then 1 times 1 plus minus 1 times 0 is also 1. So we'll get a 1 down the bottom here. And of course, this thing is 1 over root 2 of our 0 state plus our 1 state, like so, okay? And then we can apply this gate to that superposition state just to check that we get back our original state, okay? So if we take our Hadamard here, 0 plus 1 on root 2. So we get 1 on root 2. Applying this to the sum is like applying it to each of them on their own. So this would be our Hadamard times 0 plus our Hadamard times 1. So this is now 1 on root 2. We know that Hadamard on 0 will give us our superposition with a plus sign in it. You're going to have to take it on faith that when you apply Hadamard to 1, you get the minus sign in there. You can prove that one for yourself as an exercise. So this will be now 0 minus 1 over root 2 just here. And if we work this out, the 0 adds to the 0, the 1 cancels out the 1. And so we've got 1 on root 2 here with 2 of the 0 state and none of the 1 state over root 2. And this is now 2 of 0 over 2. Root 2 times root 2 is 2. And of course, this thing is our 0 state back again, okay? And I'll let you play around with this for yourself. So you can prove that Hadamard on 1 gives you this. You can prove that if you apply Hadamard to this thing, you will get back your 1, okay? If you look in the logic I just did there, it will change the sign just here on you. Which will then mean that the 1s add together and the 0s cancel each other out, so you get that back, okay? And I'll let you do as an exercise for yourself the general state if you've got some arbitrary superposition already of alpha and beta and what you'll get in a new case, okay? So this one's kind of nice. And what you'll notice is that if you apply it twice, you get your original state back, right? So we started in the beginning here with a 0 state. And when we applied it twice, we got our 0 state back again. This is part of a general property for logic gates in quantum computation, which is that they're all unitary, okay? And so what this means is that if we take gate and apply it twice, we always get our identity matrix back. And it's connected to a deeper requirement, which is that those matrices are unitary. In other words, the operator times its Hermitian conjugate is equal to the identity matrix. Now, the reason why we can drop this conjugate in the middle here is because all of our operators are Hermitian, which means that the conjugate is equal to the operator itself. So if we apply that operator twice, we will get the identity matrix popping out, okay? All this really says is that everything we do in quantum computation conserves normalization, okay? So we're not going to use any operators that are going to make probability become a misbehaving thing. But let me just very quickly walk through and show that this is really the case without having to do it directly above. So this would be equivalent of doing h times h. So this would now be 1 over root 2, 1, 1, 1 minus 1. 1 on root 2, 1, 1, 1 minus 1. We multiply this up, so this will now be 1 over root 2 times 1 over root 2 is a half. We can do the multiplication on the matrices. So this would now be 1 times, so we go for row for 1 to columns for the next, right? So it's going to be 1 times 1 plus 1 times 1 is 2. Then 1 times 1 plus 1 times minus 1 is 0. Then we do the next one across. So this is going to be 1 times 1 plus minus 1 times 1 is 0. And then 1 times 1 plus minus 1 times minus 1 is 2. Okay, so we get like this. Apply the half out the front, and sure enough, we get our identity matrix 1, 0, 0, 1 in here. Okay, and so all quantum gates will obey exactly this relationship that we have in here. You can go back and test this for controlled NOT for yourself as well, okay? Or sorry, quantum NOT. for yourself. All right. So before we get into looking at more than one bit operations, I just want to do a very quick warning on a couple of aspects that connect to sort of building up circuits for quantum logic. Okay, so one is if you see the gate sequence looking like this below, so this would be bit comes in, goes through the Hadamard gate first, and then goes through the quantum NOT gate second. So this would be take the bit, make a superposition, and then swap the two bits around. In that sequence that you see there, the operator sequence that you have to write mathematically to do this will actually be the two letters the opposite way around. And the reason for that is that the operators act on kets in the order that goes from closest to the ket first. Okay, so the first operation we see here is the Hadamard gate. So H would be the first operator. And then the next operation we would see would be our quantum NOT. And so that would be the X in front, okay? So it'd be XH psi that we would have for this sequence, not HX, okay? Really common amateur error in quantum computation is just to assume that you write down the operators in the same order that you see them in the circuit. Bad fatal error, okay? They always end up reversing themselves. One of the last single qubit gates I need to deal with is a thing called the measurement gate. If you think back to classical logic, because we're dealing with classical bits, you can measure the state of that bit, whether it's a 1 or a 0, without changing the state of that bit, okay? So you don't really need a measurement gate in classical logic because it's a kind of trivial operation. In quantum computation, you need to be able to distinguish qubits that are still reliably in a superposition state, i.e. they haven't been measured yet, from qubits that have been measured and now the superposition is broken and they're either in a spin up or a spin down. And that operation of measurement essentially converts what is a qubit to a classical bit by removing the superposition from it. And we want to represent that in two different ways, okay? So you can imagine we have a qubit coming in, and because it still retains its quantum character, it's represented by a single line. We then have what we call a measurement gate, which is the act of actually measuring the spin. You can imagine we just put a Stern-Gerlach apparatus in there and just measure, is it up or is it down? And then after that, we know that we've changed that state. And so we represent that post-measurement state via a different wire, which is just double wire. And that enables us to know that we have a qubit that no longer is the same information that came into that gate, okay? As a part of a measurement, we usually junk the qubit. So, after we do this, that thing will basically just go into a meter and tell us the answer. We won't use that for any more calculations because by doing the measurement, we've actually broken that qubit, okay? And this is probably the one biggest technical challenge when you think about quantum computation, which is how do you implement logic and even interactions between bits in such a way that you don't make a measurement and destroy the superposition or entanglement that you have in that bit or set of bits, okay? It'd be a long series of lectures to talk about exactly how that's done, but for this, all you really need to think about is you need to be able to distinguish between a qubit that hasn't been measured and a qubit that has been measured. Okay, so in quantum logic, same as in classical logic, there's a limited amount of things you can do with one single bit. In quantum logic, because there's a large number of single bit logic gates, you can do more than you can in classical logic. But in both cases, you want to be able to have multiple bits and you want to be able to start to do big calculations with them. So that means that you need logic gates that are multi-bit logic gates. If we think back to classical logic for a second, you probably know of two of them. One's called OR, one's called AND they're fairly simple. They take two inputs in and spit one output out, depending on the state of the two inputs. So for OR, you're asking the question A or B is A or B 1? If it's 1, if A or B is 1, then it's 1, right? So if you've got 0, 0 coming in, neither of them is 1, so you get a 0. 1 and 0, one of them is 1, so you'll get a 1. 0, 1, same answer. And 1 and 1, one of them is a 1, so, well, because both of them are 1, so you'll get a 1 on the outside, okay? You can imagine having the same thing for quantum computation. And so what I'm going to do is show you the one most important multi-qubit gate, and it's a thing called the controlled NOT, okay? And so you might have heard me in the video earlier slip quantum NOT in, or mistake quantum NOT for controlled NOT. It's a really easy thing to slip up sometimes. So quantum NOT is a single bit gate that just flips the bits. Controlled NOT is a multi-qubit gate that acts as follows. You have two qubits come in. One is called the control qubit and the other one's called the target qubit. The way that the quantum NOT is applied to the target qubit depends on the state of the control qubit, okay? Now, this has to be done in such a way that you don't actually make a measurement in this. So what you're relying on is your two quantum bits interacting with each other without you actually having to do a measurement externally to drive which way this works, okay? So it's a bit of a technical challenge to make a controlled NOT gate. And back in the early 2000s, there was a lot of work in how do you make this and how do we know that we can even make this? Turns out you can, because we now have quantum computers where controlled NOT is one of the foundational parts, as we'll talk about in a few slides from now. Now, if you remember back to lecture 7 and 8, you are now in a situation where we've actually got two bits. So we start being able to deal with sort of our dual spin spaces, okay? So you might have states which are 0, 0, 0, 1, 1, 0, and 1, 1, which correspond to the state of this bit and the state of this bit combined together, okay? So sort of this Alice and Bob idea that we had earlier. So the way controlled NOT works, and I'll do the maths for how this works in a slide from now. The way this works is the action of the NOT depends on the state of the control bit. If the control bit is 0, what it will do is let the target qubit through unaffected, okay? So for 0 on the control qubit, the target qubit's unaffected, so 0, 0 goes to 0, 0, 1 goes to 0, 1. If the control qubit is a 1, then the target qubit will have a quantum NOT implemented on it. So for the 1 on the first bit here, the second bit will be flipped. So 1, 0 becomes 1, 1, and 1, 1 becomes 1, 0. Okay, and this is why it's called controlled NOT, because whether or not the target qubit has a quantum NOT applied to it is determined by the state of the control qubit. Okay, whether or not the NOT is a NOT. It's a nice pun there. Okay, and then you can imagine you can take this on with superposition states. So if you have a superposition here like this one, so some amount of 0, 0, some amount of 0, 1, some amount of 1, 0, some amount of 1, 1. And of course, these prefactors here are normalized. So as you see up here, the sum of all the prefactors is equal to 1, just to keep probability sensible. What happens when you apply a controlled NOT is that if the first state is 0, then the second state stays the same. So you'll notice that alpha 0, 0 stays as alpha 0, 0, and beta 0, 1 stays as beta 0, 1. And then for the 1 in the first qubit, it will flip the second one. Okay, so our 1, 0 here now becomes 1, 1. So it takes on the delta prefactor, and the 1, 1 state takes on the gamma prefactor. Okay, we basically just do a bit swap on the ones with the 1 in it. So now we have enough gates to do something useful, which is to generate entanglement. So let's put some gates together in a sequence that looks a little bit like this. What we have is 2 bits, both 0. We pass the first bit through a Hadamard gate to generate a superposition, and then we use that superposition to drive a controlled NOT on the remaining bit. And so let's just work through the logic first to show you that this ends up giving us an entangled state, which is the triplet-plus state, 1 1 plus 0 0 plus 1 1 over root 2. Okay, so you'll remember that the action of our Hadamard gate is to basically take a 0 and turn it into a 0 plus 1 on root 2. Okay, so if we think about our system as we have it here, we now have to account for 2 bits. So we're going to start out with a state that is 0 0. And then what we're going to do is act the Hadamard gate on just the first of the 2 bits. Okay, so it will just work on that first bit label. So now what we would do is going to get some mixture of 0 in the first label and 1 in the first label, with the second bit basically just hanging on the back as a passenger. Okay, so the way this will look is as 0 0 plus 1 0 on root 2. Okay, so if you compare that to the line above, you'll notice that all I've really done is just appended a second bit 0 in the right hand side of all the kets, just to carry this line here. Okay, so we're now at this point here in the logic circuit, and what we would do is apply a controlled NOT. Right, so that's the action of our Hadamard. Let's have the action now of our CNOT. And so our CNOT gate here will basically determine the state of the second qubit on the basis of the state of the first qubit. And we know if the first qubit is 0, the second qubit gets left alone. So it will remain as 0 and 0. And if the state of the first qubit is 1, we will flip the state of the second qubit. So 1 0 will become 1 1. And we keep our normalization. And this, of course, is our triplet-plus state, all right? So what we do here is have a nice little circuit that takes 2 independent qubits, both set to 0, does a superposition on the first, and then uses control NOT to build us a entangled state in the second. And so you'll remember back in lectures 7 or 8, we were like, how do you generate entanglement? This is how you generate entanglement, okay? You basically, from a logical perspective, you take 1 bit, you make a superposition, you use that superposition to run a controlled NOT on the second bit, and that gets you an entangled state. Nice and easy, okay? Just to satisfy all the students who have been asking me in my own course, how does the mathematics work when you have more than 1 bit? I'm actually going to go through and just look at this from the operator perspective real quick, okay? I'm not going to drill down into this really slow because it'll take me all day. I'm going to rip through it. Those of you who've seen my course and understand how the maths works, this should probably make sense straight off the bat. So what we're going to do is write our state 0 0 as a vector, and that vector is basically going to have 4 elements in it, because now there's 4 possible states, right? So this thing is going to be 1 0 0 0, like so. And some of you will go, well, hang on a second, isn't 0 up, and so it should be 0 1 0 1. That's not true, because not what we're doing is not saying let's take the vector of 1 and append the vector of the bottom, the vector of the other one on the bottom. What we're doing here is saying what are the distinct possible states of the system, and what is the balance of those states. So this thing should really be seen as a vector that looks like this: 0 0 0 1 1 0 and 1 1, like so. And of course, because we're in the 0 0 state, this is going to be the only one that is non-zero, and it's going to be equal 1 to preserve normalization. Okay, so that's probably the first big hurdle that you have in terms of dealing with the mathematics of dual spin states, is just that understanding of what the vector actually is there. Our controlled NOT is now a matrix, and because there's a 4x1 vector, we now have a 4x4 matrix that we have to work with. And I'm not going to go through exactly how we arrive at this form for it. I'm just going to write it down. But if you think your way through the actions of controlled NOT, this whole matrix will probably make some sense, right? So this is going to be 1 0 0 1, so identity matrix in the top corner. The bottom right corner is basically going to be a bit swap. So it's going to be the equivalent of our quantum NOT gate. So it will now be what would look like sigma x. And then we've got another 8 elements in this matrix, and we are going to switch them off. So they're going to be 0, 0, 0, 0 in here, and 0, 0, 0, 0 in here. And a lot of students at this point usually ask me, well, hang on a second, what happens if you take those two in the opposite corners and you make them something else? I'll let you play around and find out what happens with that for yourself, okay? There actually is really useful purpose for that. We'll see that in a moment when we get to our Hadamard Gate. You can do things with those other two blocks. Actually, let's get straight to Hadamard Gate, looking at my notes. So the Hadamard Gate can act on the top because it's a single qubit gate, or it can act on the bottom. So we would have two different matrices depending on where that Hadamard Gate is. And the H top, so this is Hadamard in the top line, is going to look a little bit like this. Let me just move this equals over. We need to carry a normalization factor out the front. I'll let you work out why that's 1 over root 2 later on. This thing is going to be the equivalent of matrix scale Hadamard operator. So the way this works is 1, 0, 0, 1. We need a 1 up here, so this is 1, 0, 0, 1. This is going to be 1, 0, 0, 1. And this down here is going to be minus 1, 0, 0, minus 1. Okay? And so if you think about this, this is like identity matrix, identity matrix, identity matrix, minus identity matrix in the corner. Okay? Again, I don't have hours to show you exactly how this teases out, but if you play with it yourself, you'll see that this thing actually works and it's a sensible way to write it. So now what we're going to do here is going through this logical sequence. We're going to apply an operator, and we should get a state at the end. Okay? So what we're going to do is get our final state for this system, and it's going to be the first operator in the sequence is the Hadamard. So it's going to be the one that's closest to the state. And then the second one is going to be the CNOT. So this would be written as CNOT, Hadamard top on our original state. Okay? Same as in the slide a couple back, you have to be careful about the order of your operators. So this thing now is 1 on root 2. Controlled NOT, actually let me write this bigger because it's going to need to be huge. Our controlled NOT is 1, 0, 0, 1, 0, 1, that's a 1 just there, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, times 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, minus 1, minus 1, 0, 0, like so, on our state that starts out as 0, 0, so it's 1, 0, 0, 0 down here. Okay, so that's our big little matrix operation that we're going to do in here, and we can work through this in steps like we normally would. So this is 1 over root 2. I'm not going to rewrite this matrix again, so just assume that this thing pops down into there. If we now go through the multiplication, it's going to be top row to the column, right? So it's going to be 1 times 1 plus 0 times 0 plus 1 times 0 plus 0 times 0 is 1. So that's our first bit. Then the second one is going to be 0 times 1 plus 1 times 0 plus 0 times 0 plus 1 times 0 is 0. So that's a 0 on that one. Then it's going to be 1 times 1 plus 0 times 0 plus minus 1 times 0 plus 0 times 0 is 1. So that gets us a 1 there. And that's going to be 0 times 1 plus 1 times 0 plus 0 times 0 plus minus 1 times 0 is 0. So that's going to get us a 0 there. Okay. So that's now what our superposition state looks like. It's basically some mixture of our states 0, 0 and 1, 0, as you saw back up on this line here. Okay. So that's now this state here, superposition. And then the last part in here is basically to take our controlled NOT and apply it to that particular state and work out what comes out the end here. Okay, so we would work across this top row first to this column. And so it'd be 1 times 1 plus 0 times 0 plus 0 times 0 plus 0 times 0 is 1. The next row is 0, 0 times 1 plus 1 times 0 plus 0 times 1 plus 0 times 0 is 0. Here's the magic part. The next row is 0, 0, 0, 1, running down a column that's 1, 0, 1, 0. So you're going to end up with products that are all 0 all the way through there. So that one knocks that out. And then the last one has 0, 0, 1, 0, running down a column that's 1, 0, 1, 1. So the 1 on the third is going to match the 1 on the third and give you a 1, which gives you this. And of course, this thing is now some mixture of our 0, 0 state, which is up there, and our 1, 1 state, which is down there, with no components of 0, 1, and 1, 0. Okay? That's how the maths works. Pretty simple, okay? We basically just take what we already know, scale it up, and away we go. And you can imagine, if you look at the Hadamard, what we did in here was we had something really simple, which is just an identity matrix in that corner. If you want to have some fun, you can play around with other things that do strange things in there, like an X or whatever, and you can see that you can get some really interesting mathematical operations popping out of operators on dual spin states. Okay, so I'll leave it as an exercise to play with because it's kind of fun to muck around with that sort of state. And so where we end up in the end here is there's a whole zoo of quantum gates that then you can build up because you've got a lot of mathematical flexibility inside this ability to have operators operating on states, okay? So there's a whole pile of single qubit operations. You know, we've seen one of them already, which is the X gate, which is our quantum knot. Seen Hadamard, which basically just makes and breaks superpositions. There's a whole pile of other ones that do various things, including partial rotations and square roots of knot and all sorts of other stuff. I'll let you explore them on your own. And then there's also a whole range of multiple qubit operations. The one that we just saw is our controlled knot. There's a whole pile of little 2-qubit operations, and there's also even 3-qubit operations. So in the next half of this lecture, you'll see, actually next slide or two, you'll see we can build a 3-qubit operation, which is basically just a controlled knot, or something called a Toffery Gate. All right. Now, I'm just going to finish on one last point with logic in this first half of the lecture. And that basically is that in classical computing, we have a central idea, which is that of universal sets. And so the idea of universal sets is that there is some minimum number of gate operations you can take that enable you to do every possible logic operation you would ever want to do. And the nice thing in classical logic is that there's two really easy universal sets. One is the not and gate, and the other one is the not or gate. And if you've done a little bit of logic, you realize that actually with some combination of just NAND gates, you can do everything you want. And, or, not or, exclusive ORs. So exclusive OR is basically where you just go, if it's 0 and 0 and 1 and 1, it's 0. And if it's 0, 1 and 1, 0, then it's 1. So you knock out the 1, 1 case, and so forth. And you can do that with NOR gates on their own as well. You can build up all these logic operations out of one type of gate. And what that means is that by ganging a whole pile of a single type of thing together, you can do very, very versatile things. From an electronics perspective, this is nice because instead of having to make electronic devices that do a whole pile of different gate operations, once you have one that does one universal gate operation, then you just got to integrate all the circuits together and you can do all sorts of things. And this is why you're really interested in universal sets for logic. There's universal sets that exist for quantum computing as well. And in quantum computing, what happens is you get a universal set out of the set of single qubit operations and controlled knot. Okay, so everything that you could ever want to do will be some mixture of controlled knots and single qubit operations with a very, very big zoo of single qubit operations available to you, including Hadamards, T gates, X gates, measurement gates, and so forth. And you build these up into big logic structures like the following. So you'd have a series of bits, you would run them through doing a whole pile of single and multi-qubit operations. At the end, you do a big string of measurements to find out what the state of all those bits are. And the state of all those bits tells you something in the context of the sequence of logic that you've done as the answer to your problem. Okay, so now we're sort of at this quantum algorithms stage. So to just give you one example, this Toffery Gate, which is basically a 3-bit controlled knot. So what happens here is the state of the 2 control bits here determines how the knot works on the 3rd target qubit. You can make that out of some big combination of single qubit gates, Hadamards and T gates. T gates are just sort of a rotation. and controlled NOTs to different lines. Okay, so you've got this idea that once you've got a minimum series of gates, you can do all sorts of things. And this was the main focus why, 10, 15 years ago, everyone was really heavily focused on how do we make controlled NOT work really well. Because as soon as you have controlled NOT, you don't really have to go to any trouble to make new multi-qubit gates, because with all your single qubit gates and controlled NOT, you can do everything you ever want to do. Okay, works quite nicely. So let's take a break here. This is about as deep into quantum computing from the logic and algorithm side as we want to get. You probably need to take a much longer course to work your way through everything that comes from here. And in the second half, what I'm going to do is jump from the logic level all the way up to the operating system level, and we'll have a little bit of fun with IBM's quantum computer. I'll see you soon.